2, 1. All right, Mimi.
Aloha, everyone! Thank you so much for joining us for another installment of the Women in Space Exploration Talk Series. We are so glad you are here with us. My name is Mimi Fuchs. I spent the last 5 years operating some of the telescopes in Mauna Kea, and now I'm back in school learning more about engineering to learn more about different ways that I can be involved in the aerospace industry. I feel so lucky that all week I've been able to hear from so many of our incredible speakers, and we are in for a treat today because this morning we are joined by Dr. Amanda Hendrix. Dr. Hendrix is a pioneering planetary scientist known for her studies of solar system bodies at ultraviolet wavelengths. Her research includes so many really exciting explorations, from moon and asteroid composition to trying to understand space weather effects and the resulting radiation. She's been a co-investigator on NASA's Cassini, Galileo, and Lunar Reconnaissance Orbiter missions. She's a PI for the Hubble Space Telescope observing programs and a principal investigator of NASA's Toolbox for Research and Exploration. She also has worked for NASA's JPL, the Jet Propulsion Laboratory, for 12 years, studying asteroids and icy moons, and was a deputy project scientist for the Cassini moon mission of Saturn. Folks, if you haven't seen photos from Cassini, after this talk, I'm sure you'll be Googling some more of them. They are just absolutely incredible. And more recently, Dr. Hendrix was even a NASA astronaut candidate finalist. So if you have questions about what it takes to try to audition, to try to become an astronaut, she is your gal. Now, for some of you, maybe you tuned into these talks and you know how they work. But for those of us who this is your first time tuning in, Dr. Hendrix is going to talk for about 30 minutes or so. Afterwards, it is your time to get all of your burning questions answered. So please join us, participate, send along your questions. There's a meeting chat window that is available to all of you throughout her presentation. So if you have an idea about something, she said something that's confusing or something that's exciting, let's ask her more about it. So send it along to the chat window. And you know, programs like this are really, we're really encouraged to get everyone excited about space, especially those young women who think that they might see themselves working in the space exploration industry. So if you're one of those participants, we really want to make sure your questions get answered. So we are going, when you send in your questions using the chat window, please include the hashtag WiSE. If you're a young woman who is an early career scientist, we definitely want to make sure we get your questions answered. Now, just as a heads up, we've experienced a little bit of technical difficulties today. So if we have those, thank you so much for your patience, for bearing with us. I know everybody has been on some virtual meetings now, especially now during the COVID pandemic. So thank you for always being so patient with us as we get everything set up. Now, I would be remiss if I didn't thank everyone who makes this talk series possible. Of course, a huge, huge mahalo to Pisces for putting on this presentation. And we're very thankful for the support of Microsoft and the Hawaii Science and Technology Museum. So with that, I'm going to be turning it over to Dr. Hendrix. And so she'll be talking for the next 30 minutes. And afterwards, we'll have an opportunity to ask her some questions. Without further ado, we're going to turn it over to Dr. Hendrix.
Hi, everybody. Thanks so much for joining. Can you hear me okay?
You sound great.
Great. Thanks. Now, my system seems to be a little bit glitchy, so I'm hoping that it seems to crash on me when I share my slides. So I'm hoping that Mimi can help out with that. Great. And I could just maybe tell you when to advance the slides. Is that okay? Should I kind of get started talking while you load them up?
Absolutely. They should be getting loaded any second now. And
there they are.
Like they're up.
Right.
So your first slide is there.
Okay, thanks so much. So, right, so I'm Amanda Hendrix. I'm really happy to be here, and I really am appreciative of the invitation to get to talk to this great group of people. like the introduction said, I have worked on a few missions throughout my career so far, and including the Cassini mission, which some of you know visited the Saturn system. It was launched in 1997, it arrived in 2004, and then the whole mission went on for 13 years until 2017. And so the orbiter was orbiting Saturn and taking great data of the planet and the environment and all of the moons. And so I feel really fortunate to have been involved in that mission. And I wanted to tell you about some of the science highlights that we learned about from the mission. So it says here that I was a Cassini UVIS co-investigator. UVIS is one of the instruments on Cassini. It's the ultraviolet imaging spectrograph. And so I'm still playing with data from that instrument because there was so much data. And I was also the deputy project scientist, which was a role that I came into after several years of being on the mission, which was kind of an oversight of all the science from all of the instruments. So that was really a great experience. Okay, next slide, please. Okay, so this is a nice, pretty graphic, not to scale, of the Cassini spacecraft in orbit around beautiful Saturn. Next slide, please. Okay, so here's the Cassini Orbiter, a couple of different views of it. And this is a NASA flagship mission. So it's a big spacecraft. We like to say that it's about the size of a school bus. And this big baby had 12 instruments on board, and they're kind of pointed out here in the blue script. That might be too small to see, but basically there's all sorts of instruments doing all sorts of different kinds of science oriented in different sides of the whole spacecraft here. There are thrusters to help orient the spacecraft in different directions, and gyros to do that as well. And then the big white cone at the top is the high gain antenna. And that was the part of the spacecraft that we had to turn toward Earth in order to downlink data to Earth, and then also uplink commands to the spacecraft and tell Cassini what we wanted it to do. So every time we wanted it to play back data, we had to turn the spacecraft toward Earth so that the high gain antenna pointed towards Earth, and then we'd have to turn it in different directions to point particular cameras toward our target. So it was pretty complicated. It's a big, complicated mission, but achieved a lot of great data. Okay, next slide, please. So, as I mentioned, there were 12 instruments on the orbiter, and they were grouped into optical remote sensing, which is basically the cameras. And these were cameras that took data, spectra, and images in different wavelength regimes, from the UV out through the far IR, so short wavelengths, visible like our eyes can see, and then longer wavelengths than our eyes can see. And then we also had the magnetospheric and particle science instruments, the MAPS instruments, and these are sensing electrons, magnetospheric waves, things that our eyes can't see but are really important for understanding fields and particles in the Saturn system. There was a radar, very important. I'll talk more about that. And well, they're all important. And then RSS is the radio science subsystem. And that instrument is basically that big high gain antenna that I told you about. When that's pointed towards Earth, for instance, and it can actually sense what the interior structure of, say, Saturn or one of the moons is like. And it can help tell us where the spacecraft actually is at any time. Okay, next slide, please. So my role on the project was to do a lot of the planning of what science activities were going to happen. And I was kind of one of the people in charge of planning out the icy satellite flybys. So Saturn has a lot of icy satellite moons, and it also has the big moon Titan. And so what we would do is every time the Cassini spacecraft flew by one of those moons, we'd have to plan out what was going to happen and which cameras and which instruments were going to look and take what kind of data at what time. And part of what's related to this is the whole timeline of the mission and the whole fact that Saturn takes about 29 years to go around the sun one time. So that means that one Saturn year is 29 Earth years. And Saturn is actually tilted on, relative, its spin axis is tilted relative to the sun, the plane where the sun is, by about the same amount, not too far off of what the Earth is. So basically, that means that Saturn and its moons have seasons, just like Earth does, not unlike Earth. And so when the Cassini spacecraft arrived at the Saturn system in 2004, it was summer in the southern hemisphere. It was winter in the northern hemisphere. And the whole plan that we worked out was that it would be a 4-year mission. So it would go from 2004 to 2008. We would do 74 orbits of Saturn and check out the moons and the rings. And then everything was going so well by 2008 that we said, hey, everything's still working. We should really stay here for longer and get even more data, do more orbits. And so we got approval to stay in orbit for another couple of years until 2010. And that was what we called the equinox mission. And that was because now Saturn is moving from southern summer, northern winter, into equinox. So the sun is going to be in the plane of the equator, just like when it turns into spring or fall here on Earth. And then at the end of 2010, everything was going so well again that we were able to get another mission extension. And this was clear out to the middle or end of 2017. And this was called the solstice mission because now we were going to see summer solstice come into the northern hemisphere. So it was really remarkable. By being there for 13 years, we were there for almost half of an entire Saturn year. So we got to see seasonal evolution on the planet and on Titan and other aspects of the system. Okay, next slide, please. So in planning out the whole mission and all the science that was going to happen, we had different science areas. And the ones that I'm mostly interested in, and then I'll tell you a little bit about today, were Titan, the big moon of Saturn, and the icy satellites. And I said I was kind of one of the people in charge of planning out the icy satellite flybys. Okay, next slide, please. So in that first 4-year prime mission, as I mentioned, we had 74 orbits. And these are a couple of plots that look kind of weird, but the left-hand one is looking down. If you are way above Saturn, above the North Pole and looking down, these are all of the orbits that were flown by the Cassini Orbiter. And you can see, and so the sun is off to the right in these plots, and so you can see that the orbits were planned so that we'd get to see all around Saturn, and with different lighting conditions. So with the sun in a relatively different spot for each of these orbits, and different sizes of orbits. So we'd get in closer to the planet, and we'd be out farther from the planet for some orbits. And then on the right-hand side, you can see the same plot, same orbits, but from the side. And so not only did we have different shaped orbits, but we also had different inclinations. So they were up at different angles, or above the equatorial plane, which is where the rings are, or below it. And that way we can have the orbit take us up, and the instruments can look down on the rings, or they can look down on the polar regions of the planet. So it was very well thought out to get all of the science that we wanted to do. And all of we call them navigation engineers at JPL, are the ones who planned out how to do this. So it was really great accomplishment. Okay, next slide, please. So then after that initial 4 years, and then we added on 2 years and another few years till 2017, this was the whole entire tour that we did. So it looks really kind of jumbly and complicated. If you go to the next slide, it kind of looks like a whole ball of yarn, really. It looks like a mess. But it was great. It was, like I said, a great job by the navigation engineers, and it really got us a ton of science. Okay, next slide, please. And this is a different way of showing for each of those 13 years in those different columns, what the season was by looking down at the bottom row there at the lighting on Saturn. And also what it shows is the number of orbits in each year. So that's the number of times that we went around Saturn, basically. And also the number of Titan flybys. Those little kind of orange balls there are all Titan. And Titan is important because it's a major science target, of course, because it's a really interesting moon. And it's one of the main reasons that we wanted to send the Cassini spacecraft to the Saturn system, is to learn about Titan. But it's also important because it's big. Like I mentioned, it's the biggest moon, but then that actually helps us dynamically to help drive the orbit and kind of perturb the orbit so that we can shape our trajectory around the planet without having to use a lot of fuel. So we can actually use Titan to help us out also. So we had a lot of Titan flybys each year. And again, each one was at slightly different geometry, slightly different altitude, slightly different longitude and latitude. And so we can really kind of map it out. And then we also wanted to do a lot of flybys of the moon Enceladus down on the next line there. I don't know if you can see my cursor, but down here is Enceladus. And we started off planning 3 flybys, but then it turns out it was so interesting that we added more flybys in the later orbits. Okay, next slide, please. So here is Enceladus. Why did we want to do flybys of Enceladus? Now, before Cassini got to Saturn, all we knew about Enceladus was from these 2 Voyager encounters, from the Voyager spacecraft that flew by in 1980 and 81. And we knew that this was what Enceladus looks like. It looks like an ice ball, basically. It's got some craters on it. And it's just kind of, we knew that it was very high albedo, which means that it's very bright and very reflective. And what also we knew was interesting was that, you know, I mentioned the craters that you can see here, but you can also see that over here, again, not sure if you can see my cursor, but on this other side here, down towards the lower right, there's not as many craters, at least at this resolution. You know, why would there be some craters up at the top part and not craters down here at this lower part? Usually, for most things in the solar system, like think about our moon, it's covered in craters, it's saturated. So why wouldn't Enceladus be saturated in craters? Generally, if something isn't saturated in craters, maybe that means that it's had some sort of geologic activity relatively recently that has erased those craters. But we know Enceladus is very small. It's only about 500 kilometers across. And so, you know, small things generally don't have geologic activity. And the other thing is that it's so bright. I mentioned that it has a very high albedo. And again, usually things in the solar system, they hang out, they're orbiting their planet, they're an asteroid and they're orbiting the sun, and they get kind of dark with time because there's lots of micrometeorites flying around and hitting them and bringing in dirt, and they get dirty with age. But Enceladus is very bright, very much like pure water ice from its spectra. Which again, why does that mean that it's been kind of covering up its surface with some sort of geologic activity over time? That was the questions that we came into this mission with. Why is Enceladus so bright, crater-free, and you know, and also it seems, well, I'll mention the E-ring of Saturn, which you know, Enceladus seems to be orbiting Saturn at the densest part of the E-ring, which is a very broad, tenuous ring of material outside of the main bright rings of Saturn. Okay, so next slide. We found out that Enceladus looks like this on one of our very first encounters with this small moon. So you can see up to the upper right, you can see some craters up there, but then down, and this is, see these blue stripes? These we came to call the tiger stripes. That's right at the South Pole. And there's no craters down there, which is weird. And the terrain looks very kind of wrinkly and like almost like there's maybe some tectonic activity going on. What are these huge fractures that are the tiger stripes? Very interesting and bizarre and not what we expected. And then next slide, please. the magnetometer on board, again, this is the instrument that senses the magnetic fields, sensed from one of those first flybys that something unusual was going on. That team came to the project and said, hey, there seems to be almost like material around the South Pole that is kind of perturbing Saturn's magnetic field lines. And everybody said, well, that's weird. And then, so what we decided, you know, with this whole 4-year tour that we had planned out, let's tweak it so that we can get closer to Enceladus on our next flyby, which then, of course, had ripple effects down for the following, you know, 60 orbits. So we changed the trajectory to getting closer to see what was going on, because this was so unusual. And so on the next slide, we also did stellar occultations, and this was the team that I worked with, the UVIS team, ultraviolet imaging spectrograph. We did a stellar occultation where we watched a star as it basically passed behind Enceladus. And can you go to the next slide, please? There should be another, there we go. Oh, I see. We watched a star pass behind kind of the equatorial region of the planet and didn't really see anything, the moon. But this was a very sensitive way of measuring gas or an atmosphere. And then we got lucky on a later flyby in 2005, we actually saw a star pass behind the South Polar region, and sure enough, sensed kind of a local atmosphere. And it turns out that the magnetometer and the UVIS were in different ways sensing this South Polar plume on the next slide that we saw later in images like these, where, you know, those tiger stripes at the South Pole are emanating water vapor and water particles, kind of like geysers here on Earth, but not exactly. And it turns out that they are they're basically sourced by a subsolar ocean, a subsurface ocean. Okay, next slide, please. Oh, there's the still, just kind of with a bluish tint to it. Next slide, please. Another interesting set of data from Enceladus was from the Cosmic Dust Analyzer, the CDA. And this was an instrument that, you know, after we discovered the South Polar plume, we decided to really change things up and go closer and closer to Enceladus and go through that plume and really measure what it's like with instruments that can like pick up the particles and smell them and taste them and see what they are and how big they are and what their distribution is like. And CDA is one of those instruments. And what they found is that some of these grains are salty. And some of these larger grains are actually salty. And so that, along with some of the modeling that was done to kind of infer the interior structure of the moon, told us that there must be a subsurface ocean on this small world. So if you can go to the next slide, this is what we think the surface of Enceladus looks like, what it looks like underneath that icy shell, basically. We think that that icy layer, that the surface layer, is maybe only 5 kilometers thick or so, and below that is an ocean. And at the floor of that ocean is a rocky seafloor. And that rocky seafloor, we have indications, may even have kind of hydrothermal vents, just like we have here on Earth. And this is really interesting because the hydrothermal vents at the ocean floor here on Earth are really kind of havens for some forms of life. They're very, they provide a lot of energy and nutrients to some forms of life. So Enceladus, surprisingly enough, for a small icy satellite, may be our best bet for looking for life in our solar system. So very interesting, and we'll have to go back and measure, make more measurements of that ocean on Enceladus. Next slide, please. I want to move on and talk about Titan, which, again, before we got to before the Cassini mission got to Titan and Saturn, this is what we knew it looked like from Voyager. Looks like a big orange ball, whereas Enceladus looks like a little white ball. Titan looks like a big orange ball. Titan is actually the second largest moon in the solar system, so it's bigger than our moon. And part of the reason it seems so big, because we actually used to think that it was actually the biggest moon, but it's got a thick atmosphere. And we cannot see through that atmosphere with our eyes. All it looks like is like orange haze. So that's the main reason that Cassini carried a radar instrument, because at those long radar wavelengths, they can penetrate and probe through that thick atmosphere and see what the surface actually looks like. So the next slide, please. This is what we learned that at least parts of the surface of Titan look like. This is actually not a radar image. This is a longer wavelength infrared image. And it looks kind of Earth-like, doesn't it? With like brighter areas and darker areas. But I don't, and it's kind of a false color. It's not really bluish like this. There are not continents on Titan, though, like on Earth. There are darker areas and brighter areas, and we still don't really know why that is. Next slide, please. One of the things that, one of the kind of tools that we carried along with us with that Cassini mission was called the Huygens probe. And on the left here, you can see the Cassini Orbiter with that big high gain antenna up at the top. And on the side there, you can see that gold foil round thing pointing out at us. And this is the Huygens probe. And by the way, this is in a thermal vac chamber at JPL. And before launch, doing some testing. And you can see down there at the lower left, there is a human in a bunny suit. And there's some other humans right below the Huygens probe with the gold foil. So that actually gives you a kind of a scale of how big this spacecraft is. But anyway, so here's the Huygens probe over on the right. And this was a whole, basically a whole separate mission almost, because it was ejected from the orbiter as we were approaching Titan back in December of 2004, and it was directed to fly into Titan's atmosphere and to make measurements as it flew through the atmosphere. Next slide, please. So this is obviously a cartoon of what it must have looked like, since nobody was actually there to witness it, of the probe coming in, getting slowed down by parachutes to land on the surface. And the whole time that it's coming down through the atmosphere, it is making measurements, taking pictures, measuring temperature, wind speed, and composition. And this is really how we know about what Titan is like in situ, at least at this place. Now you can see here, even though this is an artist's rendition, it's probably fairly accurate because you can see Saturn off in the distance. It's kind of hazy because there's a hazy atmosphere that we can't really see through with our eyes very well. And that atmosphere was the whole reason that we could use a parachute to help slow down the probe as it landed. And also, this atmosphere is related to the fact that we didn't actually know if the probe was going to land in liquid or on a solid surface, because there were predictions that Titan would have a global surface ocean, actually. And this is because of the hydrocarbon chemistry that we know must be happening in the atmosphere. Now, the surface ocean that was predicted, it turns out it isn't there. The probe landed on a solid surface, although it turns out that it probably bounced a little bit and it may have been slightly damp. Like it kind of like if you throw something on a wet sponge and a little bit of moisture comes out, it might have been a little bit like that. Next slide, please. Here's an image of the landing site. So everything looks all kind of orange like the atmosphere does. The skyline looks kind of orange, and you can see that the surface all looks kind of orange. And interestingly, those rocks that you can see which are water ice rocks. Those are a few centimeters across each, probably just for scale. They seem to be coated in this orange stuff, and it's all hydrocarbons. So what I mean by hydrocarbons is molecules like methane, which is CH4, and this is all related to the atmospheric chemistry that's happening. And the whole reason that the atmosphere is kind of orangish is because there's a little bit of methane mixed with the mostly nitrogen that the atmosphere is made of. And it makes hydrocarbon molecules, larger chain hydrocarbon molecules that are much larger and turn into haze particles. I think on my next slide, or coming up at some point, oh, I'll show it to you in a couple slides. The atmosphere, that's okay, keep going on this one, please. The atmosphere means that there's weather. Remember, we've got seasons on Titan and we've got weather because of the atmosphere. There are clouds that are formed, like you can see here. Those brighter white areas are not always there on Titan. They were clouds that formed, and we saw evidence of rain coming out of those clouds because we could see that the cloud moved by and that the surface was darker and evidently damper, and then it dried out later on. So that atmosphere has clouds, it makes rain. We know that there's swampy areas, especially at the low latitude. Next slide, please. And we also know, these are, okay, that there's a lot of water ice. So even though Titan is, it's a little different from the rest of the icy satellites, like Enceladus, you know, you could see the ice right there on the surface. Titan's ice is more underneath all of that orange gunk on the surface. But Titan also has a subsurface ocean. It is also an ocean world. This is a cartoon drawing of what we think the interior structure of Titan is like. We've got the hydrocarbon-rich surface, you know, in a relatively thin layer on water ice. So frozen ice, and then below a layer of water ice is liquid water, that darker blue layer that you can see there. And then below that is more water ice, and then kind of a rocky mixture making up the bulk of the interior. So there's definitely a lot of water ice on Titan. Next slide, please. Okay. One thing that's really exciting is that there is a follow-on mission going to Titan. It's called Dragonfly, and it's going to launch in, I think, 2027. And but it's definitely still in development. And what's going to happen is Dragonfly is a quadcopter. And so it is going to be able to, again, utilize the presence of this nitrogen hydrocarbon atmosphere, which, by the way, is quite dense. It's about 5 times denser than Earth's atmosphere, but the surface pressure is about 1.5 times Earth's surface pressure. So if you were standing on Titan, you would feel only a little bit more air pressure than you feel standing on Earth. You know, whereas, say, going back to Enceladus, there's basically no atmosphere. So you would definitely have to, you know, like wear a pressure suit like you would on the moon. On Titan, you would not have to wear a pressure suit. There's plenty of atmospheric pressure. So this quadcopter is going to utilize that atmosphere and fly around just like a helicopter does here on Earth. And it's going to fly from place to place and do science measurements at each location and try to understand the organic material, that hydrocarbon-rich material that we know is the reason for all of that orangey stuff in the atmosphere and on the surface. And we'll try to find out, you know, could there be any sort of life that could be, could find Titan habitable? You know, we don't know, but certainly, you know, life as we know it here on Earth likes organic material, and Titan has plenty of that. Next slide, please. Okay, so this is this is a slide that kind of describes some of the chemistry that goes on. And this is what I was wanting to show you about the atmosphere and how it gets so hazy. So, and it just has to do with the chemistry that goes on. So it's mainly nitrogen in the atmosphere, and there's a little methane, like I said, CH4. And here's little drawings of the nitrogen and methane molecules. And what happens is when photons come in from the sun and energetic particles like electrons come in to the top of the atmosphere, they can interact with these particles. And then the particles will become bigger, more complex hydrocarbons, and they get bigger and heavier. And then they want to settle down through the atmosphere. They'll settle into haze layers. It's kind of makes the atmosphere look very smoggy, like when it's smoggy here on Earth and you can't see through it. It's because it's hazy. And that's how it is on Titan too. But those aerosols, those large particles, will get so heavy that they'll settle down onto the surface. And that's why there's that orange covering all over the surface. It's because that orange atmosphere and the chemistry that happens in it kind of ends up settling out on the surface. It's not quite rain, even though it does rain on Titan. It's a different process. Okay, next slide, please. Oh, another effect of the atmosphere is wind. And the reason that we know that there's wind on Titan is because we see dunes. So I don't know if any of you have been to dune fields. I'm guessing maybe you have. But here's some radar images of dune fields on Titan. And you can see they kind of look kind of stripy, and you can see the scale bar there. On the next slide, I think I've got some Earth, an overlay of an Earth dune field. Yeah, so here's some dunes in Africa here on Earth. And you can see that they're at about the same scale, and they look about the same as the ones on Titan. So this gives us kind of an analog for understanding what's happening on Titan. Okay, next slide, please. One of the really, really exciting things about Titan is even though there is not a global ocean as was predicted, there is actually liquid on the surface. And we know this from a couple of different ways. This lower left-hand image is a part of a radar map where the darker stuff is smoother in radar and looks like a lake. And sure enough, we did a special experiment where we were able to measure the glint off of that liquid. It's up at the North Polar region. We could see the sunlight reflecting off it and coming back into the instruments on Cassini, and it's a glint, just like we see here on Earth off of liquid. When you're in an airplane and flying over and you get a glint, same exact thing. And that kind of proves to us that it's actually liquid. And so, next slide. Titan is the only place in the solar system, other than the Earth, that has stable liquids on the surface. And they're lakes all over the North Polar region, and even somewhere on the South Pole too. This is a radar false color image showing these lakes all over the surface. They look like lakes in like, Minnesota or something here on Earth. It's very remarkable. What do you think they're made out of? Water? I don't think so, because it is cold out there. It is only about 90 Kelvin, which is like minus 250 Fahrenheit or something, even colder. And so it's very cold there. All the water, like we talked about, is frozen. These are hydrocarbon lakes, like methane and ethane, rains out of the atmosphere and is stable liquid on the surface. So it was predicted that there would be a global methane or ethane ocean on the surface. Turns out that there's just lakes on the surface. And here's another radar map. Next slide, please. Okay, here's kind of a full-up radar map of the North Polar region. So there's small lakes that you can see dotted all over, and then the larger lakes are actually, we call them seas because they're so big. So this is one reason why Titan is just so remarkable, again, and so Earth-like, really. So again, the only other place besides Earth in the solar system with stable liquids. It's got seasons, weather, rain, wind, and it looks Earth-like even if you're there on the surface. So really, really remarkable. I think of it as the most Earth-like place in the solar system other than the Earth. Next slide, please. Oh, this is the final set of orbits we did to end the mission. We needed to end the mission, so we got in really close to the planet. We went just outside the rings for a few orbits, and then we decided to get really brave and go inside the rings, so between the rings and the top of the atmosphere of the planet to get in really close. And then so that way on our final orbit, we could just tweak it a little bit and come into the atmosphere, basically, to kind of sadly end the mission. Next slide, please. Oh, okay, so this is the final, this is what it might have looked like on the final few seconds. This was September 17, I think, 2017. The spacecraft was going relative to Saturn about 31 kilometers a second. So it was really going fast. And so when it kind of started interacting with the atmosphere, it didn't take too much to actually make the spacecraft tumble. And then from all that heat, it probably would have just melted. But that was the end of the mission. It was very successful and really wonderful to work on. Next slide, please, which might be my last slide. Okay, farewell to the Saturn system. This is one of our final mosaics of Saturn that we took. Beautiful. And then I think the next one is my last slide. I just kind of wanted to briefly get back to Titan because it's such an interesting place and so Earth-like that, you know, some colleagues and I got to thinking, wow, this is so Earth-like that maybe this is actually the best place in the solar system for humans to actually settle if we want to actually set up a self-sustaining colony somewhere in the solar system. And the main reason why it's so possible to do this on Titan is because of that thick atmosphere. And that's primarily because that thick atmosphere, not only does it provide atmospheric pressure, so you don't need to wear a pressure suit, but it shields anybody on the surface from all that dangerous radiation that's out there, and especially not just solar radiation, but galactic cosmic rays that are so energetic that they can plow right through human tissue, and so they're really dangerous. But that atmosphere shields the surface of Titan from those dangerous particles, and it's the only place in the solar system with a solid surface anyway that that happens. Plus, with the atmosphere, you can fly. You could fly a quadcopter like the Dragonfly mission, but you can also, because it's low gravity, because it's a small moon, I mean, only a little bit larger than Earth's moon, and actually less dense, so it's a little bit less gravity than Earth's moon. And with that dense atmosphere, you can just fly even by flapping your arms. So it would be a hoot. Or you can make an aircraft or strap wings on your arms and fly around. So you can fly, you can, you know, go boating on the lakes, and there's a lot of resources. So you can, this is why it's self-sustaining, is that there, not only could you, you know, use the water to help make oxygen to breathe, and also to do combustion on the hydrocarbons there, just like we do here on Earth. You can harness the wind, you can harness solar power, and you can even do like methanogenic power, kind of like we do hydropower here on Earth. So a lot of options. And so we kind of wrote about some of these things in this book, Beyond Earth, that was kind of a fun little exploration of where humans might go in the solar system. And I am going to close it there and hope we have time for some questions. Thank you so much.
Definitely. Thank you so much, Dr. Hendrix. I feel like my mouth was just agog the entire time you were speaking. Particularly, I've always been just so intrigued by these geyser-like formations we see on Enceladus. And so I'm really excited we have some time to answer some questions after such an awesome presentation. And clearly the folks who are tuning in are just as excited about Titan as you are. Maybe not as excited, but clearly would like to know more. So I have a few questions I'll pass along your way that are a little bit more about like these details of Titan. So can you remind us, we saw some of these surface photos. How far above the surface of Titan did the Cassini mission go? Are you very close? Or are you very far away?
From Titan? Okay, let me try to remember. We would do from Enceladus, we actually got, our closest flyby was 25 kilometers from the surface. So very close, on a 500-kilometer body. On Titan, we didn't get that close because we could not get down into the atmosphere.
Right.
Otherwise, that would make the spacecraft start to tumble. But I want to say that we were, and I might have to double check on this, but I want to say that we were, you know, maybe 500, on a lot of the flybys, maybe 500 kilometers up above the surface.
Wow.
So,
and you know, it's so challenging to be doing these types of missions always, but particularly for icy bodies that are so far away. So how long did it take the mission actually leave Earth and get close enough to start giving us data on Saturn and nearby icy bodies?
Right, good question, because it is far away. I mean, the Saturn system is 9 or 10 AU, so 9 or 10 times as far from the sun as the Earth is. So it's really out there, and it took us 7 years to get there. But we kind of took the long way because we kind of did a inner planet gravitational assist. We flew by the Earth and Venus a couple of times, and then that helped swing us out there and give us some energy to get out there. But it took 7 years. And then the other thing is that's interesting is it took about an hour and a half, anywhere between about 80 and 100 minutes of one-way light time. So that means that the signal that was sent from Earth to Cassini to say, okay, here, do these commands now, took about 90 minutes. And same for the data coming back. Yeah.
So you have to have a lot of patience when you're working with these, you know, outer solar system objects.
Well, and we had to have a lot of patience too, because, you know, we planned out the whole 4 years of the mission in advance.
Right.
That's why any little tweak that we wanted to make had effects down the, you know, kind of rippled down. But, you know, we wanted to have everything in the can so that we could just upload bits and pieces of it at a time.
Right. So you showed us this photo, or at least a model of what we think Titan looks like as we look at the different layers from the surface going to the core. And you've talked about how potentially there's this water ice there, which is really exciting. Could future missions drill down and get a sample? Is that something that's feasible, or is it too far down?
Right. Good question. So on Titan, the water ice is just at the surface, so we can definitely access that. And as a matter of fact, there's even areas that we know, you know, even though the surface is covered mostly by organics, we know that there's areas where there's some exposed water ice. What's really interesting is whether some of those exposed or close to being exposed water ice areas could ever melt, at least temporarily. Like one can imagine that you could melt them maybe with an impact. Maybe an impactor comes in, brings in a lot of heat, melts it, and then you've got liquid water interacting with these organics. How long would that need to go on for, you know, life to take hold? Or could that have happened in the past and we can find evidence of frozen life? I don't know. I don't think it's completely out of the question, although it sounds a little bit wacky. But anyway, so more to your point, we can access the water ice easily on Titan. Getting down to the liquid water would be a little more hard because that ice layer that sits on top of the liquid is probably pretty thick, like tens of kilometers thick. But on Enceladus, it's probably only 5 kilometers of ice sitting on top of that. So that's definitely accessible. And especially down where at the South Pole where there are those fractures and, you know, ocean stuff is just coming out at us. So Enceladus, in terms of, you know, trying to visit an ocean world and see if there's any life in that ocean, Enceladus really makes it easy for us because it's just spewing out its ocean material. And so you can imagine a mission, a spacecraft that flies through that plume, like Cassini did, but with life detecting instruments on board. We didn't carry them on Cassini because we had no idea that's what we were in for. life detection instruments on a spacecraft that flies through the Plume, and maybe then it comes around and flies through again and collects a lot of samples. And probably what it would be looking for would be dead bugs, because by the time they get ejected out into, you know, the vacuum of space, they'd be dead. But wouldn't that be neat to, that would be a good clue, like, okay, there's dead bugs, so they might be live bugs in the ocean. Now let's take another mission, land on the surface, get into those fractures, and you know, get into that liquid water.
That would be so cool.
The place to do that. I mean, that ocean is so accessible.
Is a place to collect those samples. Though I will say, we keep having these questions on Titan. We clearly have participants who've read your book, and so we have two questions related to that. Okay. One is referencing potentially using methane from the lakes as a source for energy. Someone mentions potentially harnessing the hydrocarbons that are part of the atmosphere. Can you just talk a little bit about that for those of us who don't know much about renewable energy? What does that mean that we could use these as potential power sources?
Yeah, okay, so there's a lot of options. And so, you know, here on Earth, we sometimes use, you know, natural gas as an energy source. And so it's basically the same thing on Titan, where you can imagine you could access some of the hydrocarbons either in liquid form or in kind of gas form in the atmosphere, grab it somehow. Maybe you've got maybe a little bit of a pipeline going or something. And then what you'd also have to do is get the oxygen to do the combustion. And that's a little bit more work than it is here on Earth, because Titan doesn't have any natural oxygen in the atmosphere, no vapor, no oxygen vapor around. So you'd have to do electrolysis, you'd have to melt the water ice, do electrolysis on it to break it up into hydrogen and oxygen, and then use that oxygen for the combustion of, say, the methane, say that you drew out of the lake. And it actually turns out, if you want to know the truth, that after going through all that, it doesn't end up producing much energy at all. However, it does produce it. It does, you know, if you set up kind of a pipeline and, you know, a process and a factory, if you wanted to, that would be a way of making energy. You can kind of streamline it. But what I really like is the idea of harnessing the wind, and maybe even we kind of know from Huygens that there's not that much wind at the surface actually, but there's more wind up at high altitude. Up high in the atmosphere, and so maybe you could have like airborne wind machines, not wind machines, but wind energy machines, and harness that wind energy, and then bring it down and use it on the surface too, maybe to heat your habitats, you know, and then of course you need to use that oxygen that you got from the electrolysis to breathe, and anyway, so.
You know, it's very fascinating to think about how the pressure of some place like Titan would be one where we wouldn't need to have a pressurized suit, but maybe just some oxygen apparatus.
And something to keep warm. Don't forget it is.
Keep warm. Sure. So you mentioned how, you know, maybe in the next decade, we're going to have helicopters that are part of this next mission to Saturn and its surrounding bodies, surrounding moon systems. So what are you most excited about with these future missions, potentially that we could learn about?
Right. I'm so excited about Dragonfly. That's going to be so cool to go to Titan. There's also, and you know, fly around to a few different
helicopter for those of us, right? That's the name of the helicopter.
Sorry. Yep. So Dragonfly, and it's going, you know, it's selected. It was a competed mission, but it is going. It's selected by NASA. There are other competitions underway, and there will be, where we know that hopefully there will be an ENCELADUS mission going. And, you know, we talked about, you know, like a Plume fly-through mission with life detection instruments. You could do that. You could have an ENCELADUS lander that lands at the South Pole and really pokes around in the cracks and tries to get at the ocean material there. You could also have something else more at Titan, is a Titan Orbiter. There's so much more that we need to learn about Titan, even though we have like those radar maps. There's regions on the surface that we haven't mapped out with radar. there's regions on the surface that we don't really understand the composition of. Like I mentioned, those bright areas and dark areas. If we took instruments that covered the right wavelengths, now that we know more about it, we can actually understand the composition a little bit more. And another big question I have is, those dunes. It's got to be hydrocarbon material. We have dunes here on Earth, and it's sand that gets blown around, right? So it must be some process like that, but it must be hydrocarbon material. And what is that really like? And, if the Huygens probe didn't measure very much wind at the surface, then does that mean that those dunes were formed by wind in some other epoch? Or they're just kind of like every so often it gets windy? Or maybe some other process, I don't know. But I'm really interested in the form in which those hydrocarbons actually, take shape. Like, is it grainy? Is it gunky? What's it really like? I want to know.
I'm so excited to find out. Thank you for helping produce these missions so that maybe a decade from now we'll have more answers on these.
A decade or maybe a couple decades.
Decades. There's something that's really, fascinating about hearing your work and thinking about how it really is a long game, right? There's so many things, and I feel like particularly in this day and age where it's instant gratification and technology allows us to have so many answers right away, but if you're exploring these icy bodies in the outer solar system, again, really takes a lot of patience and hard work.
It takes a lot of patience, but boy, is it gratifying when it really happens. And like I said, Cassini produced so much data. It was there for 13 years. So for the rest of my career, I'm going to be looking at data of the icy satellites in Titan and just, having fun playing with the data, writing papers, figuring out what these guys are made out of and so forth.
It's so exciting. And actually, we're going to turn to our final questions.
Okay.
And this is about you as a planetary scientist. I mean, you've been a pioneer in this field where we didn't really expect there to be so many exoplanets or just so many variety necessarily of the bodies that we have. Or maybe we dreamt of it, but we didn't have the data to support it. So do you ever study exoplanets? Is this, how do you see the field maybe changing? Do you feel like what you're learning about Saturn is directly going to be applied to the field of exoplanets?
Right. No, that's a great question. Exoplanets are really interesting. And I've kind of dipped my toe into that area a little bit, but clearly it's a big field. There's a lot of exoplanets. And so I hope to get into them even more because you can learn a lot about, one of the things about exoplanets is trying to understand from atmospheric signatures, if there's any sort of life or even geology going on. Everybody wants to find an Earth-like planet. And like I said, hey, maybe one of the best places to look for Earth is right here in our solar system. For life is right here in our solar system. But, we also can think, well, at Enceladus or Titan, it's not really going to be, like humans walking around. But maybe we will find more, human-like life on some Earth-like body somewhere else. So everybody wants to find an Earth-like rocky body. But the whole idea of life being in these environments that we didn't even expect, even here in our solar system, kind of expands our thinking on where we should be looking for life or bodies that can host life in some of these exoplanet systems. But what we can do is look at the atmospheres of these bodies and try to see if they're telling us anything, if there's any clues in the spectra that there's something on the surface of the planet that is, or maybe on their moons, that is, producing signatures that because there's life there. And that's the other thing is not only are we interested in those exoplanets, but also exomoons, because again, here in our solar system, the moons are kind of where it's at.
Oh, so exciting. And we have these new results of potentially having microbial life on Venus, that potentially this phosphine signature. So it feels like the more we learn, the more exciting we find even our solar system to be.
Yep.
So I said that was going to be the last question, but our last question really is going to be about your career as a planetary scientist. Looking back, is there something that you think really helped you get to where you are today? And what advice would you give for folks maybe who are high school or are in college who are looking to be aspiring planetary scientists?
Well, first of all, my first advice is do it for sure, because it's so fun. You know, when I started out and I was, you know, in grade school and everything, I kind of knew I wanted to do something involving space. And I did want to be an astronaut. So as was mentioned, I, you know, applied to be an astronaut. I'm really glad that I became a planetary scientist, because I kind of took a windy road to get there. I started out in physics, and then I kind of changed to engineering, and all of that kind of winding around a little bit and trying to find what exactly it was that I was looking for helped give me more experience. And, you know, I basically have degrees in engineering, but with a focus in planetary science. And that kind of has helped my career in terms of, for instance, working on missions. You know, having an engineering background helps with that. So, I mean, I think my main advice is to kind of do what feels right to you. If you start going in a direction that doesn't feel quite right, you know, ask for help. Ask your advisors, ask your professors, your teachers. You know, this isn't exactly what I had in mind. I really want to do this. You know, like I was taking aerospace engineering courses, and it wasn't quite what I was wanting to do. I told one of my professors, I want to do like space. I want to do space, deep space probes. And you know, he goes, oh, okay, well, let me set you up at JPL on a summer internship. And I was like, perfect. That's exactly what I wanted. So, you know, I mean, it's just, I just feel like it's really important to stick with your gut and do what feels right and ask for help. Because that's what your professors and your counselors and your teachers are there to do, is really to help you get on the road that is right for you.
And most mentors and teachers want to help, right?
Yep.
It's a nice reminder that it really takes a community to help support one another, right?
Yep. And very few people, you know, have a very straight path to where they're going. You know, sometimes it takes a few turns and kinks, and that's part of the fun, really.
Totally. Dr. Hendrix, how can folks continue to follow your work? Is there social media handles that they could start following that allows us to see what you're up to?
I have a web, so I don't know if you mentioned this, but I'm with Planetary Science Institute, which is psi.edu, and I have a page on there where I sometimes post some of the things that I've been doing. And I also am on Facebook. You can look for me on Facebook. And I'm on Twitter also at Dr. Hendrix, although I'll admit I need to be a little bit more active on Twitter. I'm sort of an occasional Twitter person.
But also, you know, we could probably follow the Planetary Science Institute as well, right? Okay.
And the other thing is there's a load of really interesting and wonderful planetary scientists there doing all sorts of neat stuff. So
awesome. Dr. Hendrix, thank you so much for spending some time with us and sharing your knowledge and getting us all really excited about future missions to Titan.
Thank you. Thanks so much for having me. It's been really fun.
Thank you. And everyone who's tuned in, the fun doesn't stop here. Remember, we're going to be by Barbara Belvisi tomorrow, the founder of the Interstellar Lab, so we can learn all about how she works trying to design closed loop villages and life support systems to generate and sustain life on Earth and beyond. And, you know, we put on these presentations to help you guys, to be interesting to you. So please, 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 if you have a moment, please fill out our survey. There's a QR code on your screen. There's also a URL link that you can follow to take you to just a very quick feedback survey so that we can help provide programming and educational opportunities that are exciting for all of you guys. Again, my name is Mimi Fuchs. It's been wonderful to spend some time with you. And of course, a huge, huge, huge mahalo to Dr. Amanda Hendrix for her wonderful presentation. And of course, thank you to Pisces for putting on this really wonderful Women in Space Exploration Talk series. And thank you to our sponsors, Microsoft and the Hawaii Science and Technology Museum. Hope to see you all tomorrow, and have a wonderful day. Mahalo.